Assalamualaikum warahmatullahi wabarakatuh. Today, I will present to you about my research. First of all, my name is Muhammad Izzudin bin Muhammad Rozai. I am from 4 SMJM. My matrix number is A17MJ3009. My supervisor name is Dr. NORHASNIDAWANI JOHARI. The title of my research is Smart Coating in Paint Industry for Corrosion Protection. First of all, I would like to explain to you the terms of corrosion. Do you know that corrosion is one of the major research areas that has been attracting the attention of researchers for over 150 years, since it is recognized as a problem causing degradation, failure, and serious accidents and hazards in many industrial processes and domestic systems. Corrosion, in their specific terms, is the deterioration of the metals due to their reaction with a corrosive element in their surroundings, such as chlorine, fluorine, carbon dioxide, and oxygen. Damage due to corrosion in terms of economic aspects include repair and maintenance costs, loss of materials, damage to equipment, and decrease in efficiency. Furthermore, corrosion damage have other social effects such as safety impacts, health impacts, and the depletion of resources. Next, self-healing coatings. Self-healing materials can be well known as materials which are capable of autonomously restoring their properties in such a manner that they can function longer as compared to similar materials without self-healing abilities. Self-healing coatings are required for the total or partial repair of coated areas damaged by aging or unexpected aggressive events. Concerning self-healing coating for corrosion protection, two main strategies have been pursued. The first one, mending of defects formed in the polymetric coating matrix via addition of polymerizable agents, and the second one, inhibition of corroding areas due to the presence of corrosion inhibitors. Inspired by many natural materials such as lotus leaves, roses, and water striders, scientists have developed water-repellent super-hydrophobic surfaces that have a wide range of applications in different fields, including self-cleaning, oil-water separation, drag reduction, corrosion resistant, water non-destructive transportation, and anti-icing. With the massive of research, the application of super-hydrophobic surface has also been extended to the field of biopharmaceuticals. Super-hydrophobic surface will have great research and industrial value with the potential for large-scale industrial production. The general construction path of a super-hydrophobic surface is to construct a rough structure on the surface of the substrate and then use a low surface energy substance to modify the rough surface. Therefore, the chemical composition and surface structure are important factors that affect the surface wettability. In recent decades, common methods for preparing microstructures on surface include chemical etching, mechanical processing, chemical vapor deposition, and electrophoretic deposition. And here comes the problem statement. Corrosion can be defined as the older problem that always occurs all over the world. Corrosion can affect metal from many aspects. As corrosion are being researched by researchers, the current application and removal of coatings would be labor-intensive and unsafe for individuals working with them. Thus, the current coatings are unable to self-heal or alert user of anomalies, thereby decreasing material survivability. And can coating withstand the temperature and surrounding survivability? The objective of this research is to study the properties of smart coating in paint industry for corrosion protection, to research and analyzing the behavior of corrosion protection and their effectiveness, to measure the contact angle and sliding angle on super hydrophobic surface. Basically, the scope of this research is to carry out the measurement of contact angle, carry out the experimental using adhesion testing, and also test the level of hardness of a coated substrate. As for the methodology, the preparation of materials and apparatus were carried out through a step-by-step procedure. In this research of study, zinc oxide was used as nanoparticles. So, the procedure of the experiment will begin with the preparation of zinc oxide nanoparticles. The zinc oxide coating preparation techniques will be shown. Following that, the glass substrates were cleaned using an ethanol solution. Using the ionized water as a rinse, the carbon steel measured at 2.5 cm times 2.5 cm. The fabrication of samples, the steps start with the 2.4 gram of zinc oxide nanoparticles and 2.5% of stearic acid were disseminated in 10 ml of 100% ethanol for 5 minutes with steady agitation at 180 rpm at 55 degrees Celsius, followed by ultrasonication at 500 watt, 20 kHz with a probe ultrasonicator. After the process, deposit resin mass of 0.6 gram and solvent were then mixed to the solution and continuously agitated for 10 minutes. The coating solution would then disseminated onto the glass substrates and angled until it coated the whole surface. The carbon steel then dried for 24 hours at room temperature. Below is the diagram for the fabrication of superhydrophobic surface. In this research, adhesion testing also will be carried out. Adhesion testing is a test to determine whether the coating will retain to the substrate during the term of its operational life. There are many types of adhesion testing such as pull-off test, tape test, scrape test, chisel test, bend test, heat quench test, and burnishing test. For this experiment, tape test was carried out in this experiment. Here are the diagram for the test. The tape test is a more formal variant of the knife test on metal substrates. Overcast in the coatings, pressure-sensitive tape is applied and removed. The X-cut tape and the cross-hatch tape test are two different types of this test. The cross-hatch tape test is designed for use in the lab on coatings that are less than 5 mm thick. Instead of an X pattern, it used a cross-hatch design. To ensure that the incisions are properly spaced and parallel, use a cutting guide or a dedicated cross-hatch cutter with various preset blades. The cut area is next inspected and assessed once the tape has been applied and removed. Adhesion tests are classified into a few classifications. Below shows the classification of adhesion test result. The first one is the 5B. The rate of adhesion is the edge of the cuts are completely smooth. None of the squares or the lattice are detached. Then 4B, which is small flakes of coatings are detached at intersections. Less than 5% of the area is affected. At 3B, small flakes of coating are detached along edges and at intersection of cuts. The area affected is 5 to 15% of the lattice. At 2B level, the coating has flaked along the edge and at parts of the squares. The affected area is 15 to 35% of the lattice. At 1B level, the coating has flaked along the edge of cuts in large ribbons and entire squares have detached. The area affected is 35 to 65% of the lattice, and at level of 0B, flaking and detachment in excess of 65%, which will result to failure. Based on the result, by analyzing the surface of the coated substrate, the water repellent, one droplet of 0.5 ml of the ionized water 20 mm from the surface bounced off the coated substrate. The water droplet reached the sample surface and departed the surface due to the direction of the surface as it reached superhydrophobic surface. The contact angle measurement and sliding angle were achieved during the experimental procedure. The water droplets bounce off on the superhydrophobic surface. Next, the The study are carried out on the surface repeatability of super hydrophobic surface, a 3D topographical image, and average rational results. A is the zinc oxide and epoxy. B is the super hydrophobic zinc oxide and epoxy. Laser scanning confocal microscopy was used to analyze the average surface roughness and 3D profile of the coated samples. Laser scanning confocal microscopy topography image of the surface of zinc oxide and epoxy and super hydrophobic zinc oxide and epoxy coatings were shown, together with average roughness findings. The average roughness of the zinc oxide epoxy surface is 2.46 micron meter as shown, which is mostly due to the coarse structures generated on its surface. Meanwhile, the average surface roughness result of super hydrophobic zinc oxide epoxy has increased to 3.77 micrometer with the addition of stearic acid to the coating, owing to the production of richer topography generated by stearic acid modification. As a result of the air trap within the rough surface interspace, the surface can achieve super hydrophobicity. The comparison of the coated zinc oxide nanoparticles and the coated commercial paint. Based on the adhesion testing using cross-hatch-tab test, using a knife to cut the surface, the coated substrate meets the requirement of the classification of adhesion test. Based on the classification standard test method for evaluating adhesion by knife, ASTM D6677, the level of classification is 4B with small flakes of coating are detached at intersection which less than 5% of the area is affected. For the conclusion and discussion, generally, a simple and effective technique that depends on a one-step solution coating deposition procedure to build a lasting super hydrophobic surface using simple equipment and ambient temperature drying without the requirement for surface treatment. The solution primarily consists of zinc oxide nanoparticles, which play a significant role in the development of a multi-scale rough structure, while epoxy is added to improve coating adhesion and mechanical robustness, and stearic acid is added as a hydrophobic agent to reduce coating surface energy with water contact angle 160.24 degrees and sliding angle at 3 degrees. The super hydrophobic surface demonstrated remarkable water repellency and self-cleaning properties. The difference in hardness was an effect from the rigid substrate which could influence the hardness measurement of thin films. Another possible reason for the softness of thick films was the greater amount of solvents retained in the thicker coatings. In general, as the solvent evaporation rate drops at the later stage of film formation, a small amount of solvents can eventually be trapped in the coating for months or years. Several other effects can also take place in thicker films, including the increase in internal stress, the porous structure, and the cohesive failure. Thicker coatings have higher internal stress built up than thinner ones. Different forms of failures can occur as consequence of internal stress. If the adhesion to the substrate is poor, the stress will cause delamination. Instead, if the adhesion is strong, the attachment will be maintained but the coating will either crack or be able to fail more easily when subjected to external stresses. For this reason, thin films can result in more severe failure in the adhesion test.